Okay, welcome to Lecture 9. Today we are going to review and repair the previous lecture on the Chang model. I made mistakes on Monday, which I'm going to try to repair. So the object lesson in this is even experienced people can make mistakes easily using dynamic programming squared and not being careful step by step in distinguishing sharply between the time zero problem, that's subproblem 2, and the time t greater than or equal to 1 problem. So here we go. So just to review, just a notation. If z is a scalar and zt is a variable at time t, I'm going to use the notation that z with a vector is going to be this entire sequence. And we're going to let z vector superscript t be the, we're going to let that be the history. And we're going to let z vector subscript t be the future. And we'll use that in notation occasionally. And then what we have, key objects in play is we're going to have an initial condition. There's going to be a representative consumer. The initial condition is the representative consumer brings a stock of unbacked or fiat currency into time zero. And what the government's going to be choosing here is a sequence of inverse growth rates many growth rates. And a Ramsey planner or time zero government is going to choose that entire sequence at time zero. It's also going to choose an entire sequence of distorting not tax rates but tax collections. Okay. And other things, that's what the government's going to choose. These are going to be linked by a government budget constraint. A household is going to choose a sequence of a sequence of consumptions and a sequence of real balances. So the household cares not about nominal balances, but about real balances. So essentially, the government is actually going to end up choosing, this and the initial condition are going to imply that it chooses a sequence of nominal balances. So the government is going to choose, in this setting, it's going to choose money growth rates, distorting tax collections, entire sequences, and it's going to choose, consequently, total nominal money supplies. And the household is going to choose these two things. And then we're going to have a competitive equilibrium. And this is the famous Calvo model. Okay. We'll review quickly what the household's problem is. And then we'll get the first order conditions for it. Then we'll frame the Ramsey problem. as it's naturally framed in a space of sequences, and then we'll Bellmanize it. And that's where I got into a little trouble. So the household problem, here's what we're going to, household's going to, has a utility functional that looks like this. It likes real money balances. And I'm going to write that like this because its holdings of money are equal to QT nominal money equals MT over PT. So that PT inverse is QT. QT is the inverse price level. Subject to this sequence of budget constraints. The household gets income. It has some real balances carried over from last period. It consumes and it has to pay the tax collections. And we're going to impose the restriction that this is less than or equal to M bar. That's a technical restriction we're going to impose for reasons I explained in class. And this is going to take M minus 1 is given. Okay. Okay, so what the government is going to choose, the government has a sequence of government budget constraints. One for each T. It faces M minus 1 as a given initial condition. We're going to impose some restrictions that HT, the inverse growth rate, is going to belong to this set pi, which is equal to pi, it's some bounded set. And this is a technical condition to get some bounded sets later. And then we could rewrite that budget constraint as we did last time, like this. Okay, good. So there we're set. And then the final thing is Chang copies Calvo and assumes as an outcome, this is an outcome, that distorting taxes or distorting subsidies lower output. And the key thing is that he's going to assume that f of x is positive, but f, the second derivative, is negative. Okay, so we discussed that in class. Okay, so to formulate the Ramsey problem, the first thing we did is we got first order conditions for the household. When we got those. And we got an Euler equation, which we could rearrange into the following form. So this is partly where we're going to So we're going to call this object here, we're going to call this theta t plus 1, following Chang. And this was equal if we were off corners. Okay. So theta t plus 1 is the marginal utility of money, marginal utility of real balances. That's what Chang calls it. And this condition has to hold for t greater than or equal to 0. T greater than or equal to 0. This condition holds. Okay. So we're going to impose this as an implementability, a sequence of implementability constraints. On the Ramsey planner. Okay. Okay. So in the interest of doing this, we're going to work on this Euler equation star, and we're going to represent star in the following way. First, I'm going to with a little work, I could rewrite it as follows. Theta t less than or equal to where and I'm going to insist that this is true for every t greater than or equal to 0, where I'm going to also insist that theta 0 is equal to u prime okay. And in addition, I'm going to have an implementability constraint that we saw earlier. Okay, so now we described in class how we're going to think of solving this equation. Again, we have these inequalities, equal if we're off the corners. Okay. So we're going to hand these. We're going to hand these equations over to our, or some version of these equations, over to our actually, I'm going to write one more equation over to our Ramsey planner that we're going to try to Bellmanize. And actually, I might as well erase this theta, these 0 subscripts, and replace these with t subscripts because those are also true. This is true for all t greater than or equal to 0. Okay. So what our Ramsey planner wants to do, again, it wants to maximize this object subject to these. And what's he going to choose? He's going to choose a, well, substitute in here. What's he going to choose? He's going to choose a C sequence, I'm sorry, an X sequence, an M sequence, an H sequence, and a well, that's it. We could think of him choosing a theta sequence too, which would be implied by that. Okay. If we want. Okay. So now this is where I went haywire last time by skipping a few steps. So we're gonna Bellmanize the Ramsey problem, and we're gonna first do two subproblems. So subproblem 1, and the notion here is this is going to apply for t greater than or equal to 1, and it's for a continuation Ramsey planner. Continuation Ramsey planner. So here theta is going to be a state variable. That's taken as given. And the Bellman equation for the continuation Ramsey planner is going to be this. It's going to be the maximize over an X, an M, an H, and a theta prime. This object, U f of X plus beta, I'm sorry, plus V of M, real balances, plus beta J, a continuation theta, and subject to these constraints. And I want to write them out in more fully than I did on Monday. How many have theta? This is our definition of theta. I'm going to have my static government budget constraint. And I'm going to have that theta prime belongs to this set omega. And I'm going to pretend that I know omega. There's going to be some set of those. Chang's paper is all about removing the pretend, but we're going to let that go for a minute. Okay, so stare at this problem a little bit. So the government, the Ramsey, continuation Ramsey planner comes in with a theta. You can deliver that theta by a mixture of X and M policies. but he has to deliver it. And then as he adjusts X and M, that's going to affect this. And then he also can choose a continuation theta prime, but it has to belong to this set. Now that's the problem. Now, subproblem 2. Let me back up just a minute before I get that. What this subproblem 1 is going to imply, it's going to imply a set of policy functions. So I'll just write like this. And these are going to be policy functions that are to apply for t greater than or equal to 1. Okay. So again, these are policy functions, and these are defined presumably for every theta belonging to this set omega. We'll come back to these in a minute. Now, subproblem 2. This is the problem of the Ramsey planar at time 0. Okay. So we're going to let h be the value of the Ramsey plan, and that's going to be equal to the max. Now, what are we maximizing over? We're choosing an initial rate of inverse money creation, an initial real balances, an initial x0, and an initial theta. We're choosing that to maximize, well, okay, where this is an initial continuation theta. And our restrictions are going to be these. This was our time 0 Euler equation. We're going to require that minus x0 is equal to m0, 1 minus h0. That's our budget constraint at time 0. And we're going to require that theta, the continuation theta, relating to omega. And what's going to, and this is what I wrote down incorrectly last time. And I did not write this down as fully as I should have. Okay. So what's going to emerge from this policy, from this problem, is going to be a choice of m0, h0, x0, and a theta. So that's what the maximizer is going to be. And then the way this is going to work, for t greater than or equal to 1, we're going to get mt equals m of theta t, and so on. xt equals x of theta t. ht equals h of theta t, and we're going to get theta t plus 1 is equal to g of theta t. This is all from subproblem 1. This is all from that. We're going to apply that for t greater than 1, starting from with theta 0 given by, with theta 1 equal to the theta, call it star, chosen by the Ramsey planner. That's the way this goes. That's the way this goes. That's the way this fits together. And then the time inconsistency is going to surface formally in the context of saying that m1 equals m of theta star is not going to equal m0. x1 equals x of theta star is not going to equal x0, and so on. That's our time inconsistency that we've seen before. So you'll notice all I've done is just by slowing down, I've just used the same procedures that we applied in chapter 19 and chapter 20 in our earlier settings. Okay, so I want to talk about a couple loose ends. First, a major one. Well, let me talk about a minor one first. So let's look at our two subproblems and our two Bellman equations. The one for the subproblem 1 that applies for times t greater than or equal to 1, and the one for times 0 that takes as given that we've solved subproblem 1 and then solves a times 0 problem. Now, something that Chang does that's very clever is he uses thetas, or continuation thetas, as a one-dimensional variable that completely summarizes or characterizes all aspects of continuation competitive equilibria that the Ramsey planner or the continuation Ramsey planner care about. In other words, theta t plus 1, by iterating this Euler equation, it's going to be some function, I'll call it theta t plus 1, of, well, the continuation vector, the continuation vector, the continuation vector so the structure, so these continuation policies are all intermediated through this theta in terms of how they affect the choice of the, or the concerns of the Ramsey planner. So that means there's actually an equivalence, there's typically an equivalence class of mt plus 1s, xt plus 1s, ht plus 1s that will yield the same theta t plus 1. And it doesn't matter, the Ramsey planner at this point is indifferent among those. So that leads to something that what Chang works in terms of is this single dimensional variable, but there actually could be multiple competitive equilibria. We don't know. Competitive equilibrium and competitive equilibrium policies that give rise to the same theta. It's just a thing to be aware of. And when we use a Brew-Pearson-Sticchetti, there can be multiple equilibria that give rise to the same value. And their machinery only recovers a subset of those equilibria. It recovers all the values, but only a subset of the equilibria. So something like that could be going on here too. Okay. So another loose end. Now this is a significant one. When we did our work, we took as given this set omega. And again, the set of omegas were, what were the set of omega? Omegas, I'll just define it loosely, as the set of thetas associated with competitive equilibria. Okay. So how do you find that set? We took it as given. And Chang has a procedure for it. And I'll tell you the heart of the procedure. Okay. Define an operator mapping candidate sets into other candidate sets. Okay, so he's going to have a strategy. This is going to be the heart of the strategy. And what's going to be key here is there's going to be this Euler equation, this thing right here, that Euler equation. That's going to play a key role. It's going to go like this. He's going to make a guess at a set of thetas and call it, I don't know, call it omega 0 and guess a big set. So these are going to be a set of thetas that's quite big. He's going to assume that this set is bounded and compact. He'll assume some technical things. And then what he's going to do is he's going to stare at the Euler equation. And what does the Euler equation do? It takes the Euler equation takes a theta prime belonging to omega 0 and it maps it into a theta. That's what that Euler equation does. Like, look at this. Well, no, it's not really true. What does it do? So, what does it do? It takes a theta belonging to theta 0 to this. So let's just stare at the Euler equation. Just stare at it. So what does that thing do? It has the form. What is it? It has a form like this. It has a form theta is equal to some function. I'll call it this. It's some function of m, x, implicitly of h, because there's other restrictions, and a theta prime. It maps next period theta and this triple of things into a theta today. So what it does, it takes a theta in that candidate set. It takes an m, x, h, and that satisfies the equation and some other equations that satisfy the Euler equation and other restrictions that we listed. And what it does is it maps it into a theta. So it does. So now to do this for every theta prime belonging to O0. Now for every different ones, you're going to get a different theta. So the consequences of this is that's going to imply that you're going to map omega 0 into another set, omega 1. These are thetas. And then now we're going to do it again. Draw theta prime from theta omega 1 now, m, x, h, that satisfy those things, and get a theta. Again, I'm satisfy the Euler equation. And build up a new set, omega 2, and so on. And now what we're going to do is we're going to hope and pray. But it turns out this procedure defines an operator that maps a set, compact set, into a set. And it turns out the operator, the mapping, is monotone. So there's going to be a version of a monotone convergence theorem that if you start with a big enough set, iterations are going to converge to a set omega, and that's going to be a set. That's going to be the set we want. The set of thetas associated with competitive equilibria. That's the basic idea. Now that's what Chang's going to do. So Chang is going to find this set. If you think about it, so it's going to start by saying, well, I just don't know what it is, but I'm going to say there's some I'm going to make a guess at what it is, and I'm going to start this procedure of drawing this. And then I'm going to work backwards. I'm going to solve the Euler equation. Okay, now that's what's going on here, and that's the start of Chang's paper. And now what he's going to do is he's going to apply this again after he adds credibility restrictions. And that will involve another state variable. So we talked a little bit about that on Monday, and it's going to be in the notes I make available. But the basic idea is going to be essentially it's going to change this line. And the idea for doing this kind of thing is due to a group, Pearson Sticchetti, all of whom are in our department. So thank you.